Okay, so good morning everyone, and myself Vikrant Saxena, and I would like to thank the organizers for giving me this opportunity to present the work we are doing at IIT Delhi. And today I am going to talk about some of our results from 2 and 3 dimensional PIC simulations which we have been carrying out, especially my students, which are actually targeting the effect of structured hydrocarbon targets, and I will tell you why structuring is helpful and how we have proposed a new structuring, novel structures on the front of the surface, which helps in enhancing the proton energy. So the work, as I said, has been carried out by my previous student, most of it by Dr. Imran Khan, who is among the audience, and some part of it is being carried out by Yasir, who is also among you. The work has been performed using a parallel PIC code epoch, which is open source code by University of Warwick. And I would also like to acknowledge the IIT HPC facility, which is called Padum. So all the simulations which I am going to present have been carried out there. So the plan of the talk is that I will introduce the topic and then I will come to the results. So I will introduce what is TNSA and how structured targets help. And I will go over the simulations which we have carried out to optimize the groove geometry as well as the dimensions. And while doing that, we have observed that there is an effect of relativistic transparency, which helps in enhancing the proton energy further. I would also mention some results, how an axial external magnetic field helps in enhancing this proton energy, cutoff energy. If I have time, then I will also briefly discuss the extension to 3 dimensions and how it affects the performance of these grooves. Finally, I will summarize. Okay, so now coming to the protons. So we are interested in accelerating protons for multiple reasons, multiple applications. Among them, high energy physics. Of course, you all know that LHC is there. They are accelerating it to very, very high energies. And then there are other applications in the intermediate or lower energy regime where we need protons of energy 150 MeV proton energy for hadron therapy, proton-based cancer therapy, and then low energy protons for imaging. So our work is mostly focused on this energy regime where we want protons to have energies of the order of 150 to 200 MeV. And the idea behind using protons is that the Bragg peak of protons or ions is very, very narrow as compared to the traditional X-rays. And if you want to treat cancerous cells deep inside the human body, then X-rays actually affects the healthy cells on the way, whereas the protons or the ions, they affect only the affected cells. Thereby, you can avoid harming the healthy cells. So that is briefly the idea that why this hadron therapy is important. Now, why plasma-based acceleration? So we know that traditional accelerators like in LSC, they use simple RF-based acceleration. But there is a limit on that because the materials, they have a breakdown limit of so the field can go around like 100 megavolt per meter. If you go beyond that, the material is not stable. So the supporting structure of accelerator itself is vulnerable to that. And that is the reason that the conventional accelerators are very large in size. Like if you want to accelerate particles to very high energies, you have to go bigger and bigger in dimensions, and that is how the cost also increase. And you might have heard the recent news that China has stopped its very ambitious plan to develop a linear collider. And the reason is that the cost was going well beyond 20 billion euros. So that is the reason that we have to find alternative ways. But anyway, we are not going to those high energies. But when you have plasma-based acceleration, the benefit is that plasma is a broken down medium already ionized. So you can have electric fields which are very, very large, several orders of magnitude. So you can go from 100 megavolt per meter to 100 gigavolt per meter, even beyond. So you can have, people have reported that 1 teravolt per meter field is also sustainable in a plasma. So this actually reduces the dimension of the accelerator. Okay, so the idea of plasma-based acceleration came from a very popular sport in West. So they call it wake surfing. So it is little bit different from wave surfing. So what do they have? They have a boat, and when the boat is moving in a water body, there is a wake behind that, and people initially they have to put some effort to go into the phase with the wake, and then once they are in the phase, they can be moving very fast with that boat, because the wake is also moving with the velocity of the boat. So the idea came long back, and none other than Professor Dawson with Toshiki Tajima, they proposed this, that if you replace this boat by a laser pulse and this water body by a plasma, so electrons can be replaced. I mean, electron can replace this surfer. So the electrons can go in phase with this wake and they can get accelerated continuously. So that idea was very beautifully undertaken, and people have done lots of experiments, lots of simulations, and so for electrons it was very good. Lot of good results have been obtained recently using the wake field acceleration. But what about ions? Can we do the same thing with ions? No, because ions are heavy and they cannot catch up with these wakes which are moving with a very high speed, relativistic speed. So we have to find alternative methods, and there are alternative methods. What do? We don't have a underdense plasma. Rather than we use a solid targets, and we irradiate them with very strong intensity lasers. So one of the mechanisms which we use for accelerating ions is called target normal sheath acceleration. So it is, as the name suggests, it is based on sheath field. And for sheath field, what we need hot electrons. So this is entirely based on efficient generation of hot electrons, energetic electrons. And of course, for generating those electrons, you need a linear polarization of the laser pulse. And the targets which are used for this, where this mechanism is dominant, is of the order of few microns. There is also an alternative mechanism called radiation pressure acceleration, where we don't have these thick targets. We have to go for a very thin target of the order of few tens of nanometers. And because we don't want hot electrons to be generated, because this mechanism is based on radiation pressure. So what we have is, we have a circularly polarized laser pulse, which causes the suppression of these hot electrons, and then this behaves as a piston. So it is based on pressure of this laser pulse, and because of the reflection of this laser pulse, we have an efficient momentum transfer. As the electrons move as a whole, the ions will follow and get accelerated to very high energies. The problem with this mechanism is that you need very high contrast lasers, because we don't want to create this pre-plasma behind the target, because that will hamper this mechanism. All right. So TNSA, this is a typical mechanism. So you have a pre-plasma which is created by the pedestal of the laser pulse, and some people also use a pre-pulse separately to create this pre-plasma, because this pre-plasma actually helps in efficiently creating hot electrons. And once these electrons are created, as the main pulse interacts with this pre-plasma, a lot of hot electrons are generated here, and then they propagate towards the rear side, creating a sheath field in the rear of this target. And this sheath field is responsible for accelerating protons. So a lot of work has been done on this. And the benefit, the positive of this mechanism is the emittance of the beam is very low. If you compare with the traditional RF LINAC in CERN, you can see several orders of magnitude lower emittance is there, the transverse emittance. The problems or the challenges are that the energies are very limited. You cannot go beyond certain cutoff energies of protons. The divergence of the beam is high, and the energy spectrum is also broad. Now there are strategies to improve that. So we have one strategy is to structure the target. So we structure the front of the target so that the coupling of the laser to the target is improved. Can also use axial magnetic field to improve the divergence, because once you have a magnetic field, the charged particles which are exiting the target from the rear, they cannot travel in the transverse direction very freely. And people have also suggested that you can replace one single laser pulse by 2 pulses of half the intensity, so that the interference improves the electric field at the front surface, thereby enhancing the generation of hot electrons and thereby increasing the cutoff. All right. So people have done a lot of work with periodic structuring, creating nanowires, nanorods, nanospheres, whatnot, on the front surface, and all of them have been shown to improve the coupling of the laser pulse. And how does it do it? It is done, one is you create some surface plasma resonance, and also you can see that the surface, the interacting surface of the target has been increased. The laser pulse interacts with a larger surface, right? So reflection is suppressed. So now what we have been doing is we have proposed that rather than using a periodic structuring, we go for a single micro size groove, a micron size groove on the front, and we wanted to investigate how does that change this coupling mechanism. So we have tried different geometries, and what we observed is, as I said, we have done this using epoch. The simulation parameters have been taken from an experiment in Gemini laser. So what we have observed is that with this different geometries, this RG stands for a rectangular groove on the front, because it's a two-dimensional picture. So what we have observed that for all the cases when we have the single groove, the energy is enhanced drastically. So this is a 20 MeV cutoff energy for flat foil, which is going up to 80 MeV for a rectangular groove. And the focusing of the electron beam is also improved quite a lot. So as you can see, for a rectangular groove, the electrons are focused towards the axis. So we tried to look at the electrons also, and what we saw that electrons, although for a triangular geometry, the electrons have a higher energy, but the divergence of electrons is much better for a rectangular groove, and that is the reason we have much better result for that particular geometry. This is the sheath field which is generated by this, and this also suggests that the sheath field is much better in the case of a rectangular groove. So we tried to optimize the dimension of the groove, and we saw that when your groove width, this vertical dimension, matches with the waist of the laser pulse, that is the optimum thickness or optimum width of the groove. And with the depth of the groove, we tried increasing the width and the depth, and we saw that the energy continuously increased. So you keep drilling in, and you see that the proton energy keeps increasing. Okay, so now what is happening here is that once you have a rectangular groove, so you can see that as the laser pulse is going in, so it is having a grazing incidence on both the upper and lower surfaces, and as it is propagating, it continuously ejects electrons from the surface of the groove, and those electrons, so you can see the Ey is generating the velocity, y velocity in electrons, ejecting the electrons, and J cross B is then pushing them in the forward direction towards the rear of the target. And these electrons can then eject outside the target, creating a very efficient sheath field. So these kind of mechanisms people have also observed in other geometries where they use tape target and they have a peeler mechanism. So laser is peeling off from both sides of the tape target, and they have also shown very effective ion acceleration. Okay, so we actually further increase the depth, and what we saw that if you keep drilling in, it is not that the energy continuously increased. What we saw that after 1 micron or so, there is a sharp increase in the cutoff energy, and after that, once if you are drilling through, if it's a complete channel, we saw that the energy is not that much. So it has come from 140 MeV to less than 80 MeV. So we try to understand that, and what we saw is that once you have around 20 nanometer of the the foil in the back, there we have a onset of RIT, relativistic induced transparency. But if you have a channel target, because there is, in fact, the TNSA itself is not working there, because what we have is, you can see that the kind of sheath field which we have is very different. So the field is only located at the two corners of the target. And if you, this sheath field is having also the effect of laser field, so we try to remove that effect by averaging it over several laser periods. And what we saw, it's a clear picture of the sheath field, quasi-static field. And you can see clearly that electric field is focused on the edges of this rear of the target, whereas in the 20 nanometer case, the field is optimum. So even around 140 femtoseconds, you can say the field is quite strong. And that is the reason we saw that these protons gain the highest cutoff energy. Okay, so this is just a brief work. So what this concerns is that once you have a flat target and you have an oblique incidence, there have been a lot of reports that because of Brunel mechanism of electron heating, you get a very, very high energy if you have, for example, this, either you have a single oblique laser pulse of the intensity, say I0, or you have two oblique laser pulses of intensity I0 by 2. So people have shown that in this case, in the cases of two oblique laser pulses, you get a very, very high cutoff energy for protons as well as ions in the film. So we tried that whether with this structure target this helps, but it doesn't. So we saw that the best case is a normal incidence of the laser pulse, and once you have an oblique incidence, it doesn't work. The reason is very clear, that if you look at this picture, when you have the laser impinging on obliquely, it does not interact, it does not have a grazing incidence, and you can see that the electrons are ejected, but they come out at two different angles. So most of the electrons will come here. Where is the angle of the oblique incidence? So we don't have efficient surface wave excitation. So that means that once you have a structure target, you cannot go for oblique incidence. Of course, experimentally you will have some deviation from the normal incidence, but we have to keep it close to normal incidence. Okay, so now we try to explore what is the effect of axial magnetic field, and the magnetic field which we are talking about is of the order of kilotesla. So what happens that when you apply this field, so first we try to look at flat foil case. So when you have flat targets, this magnetic field which you apply, it also generates an additional field, and as a result, in the region near the axis, there is no magnetic field, so it's almost zero. And whereas at the two sides, you have a strong field. So the electrons are actually, they are, what the electrons here, they, of course, they have some divergence, but they cannot go to very large extent. And what we found by following the trajectories of say 1,000 of them, and we saw that there are principally four populations, electron populations. One, the population which remains inside the target, so it goes up to the edge, but it remains confined. The other, in this case, you can see they go out, but they come back to the target, and they are trapped within the boundary of the target. This is the third. The third population is actually responsible for the sheath field, because they are trapped near the target, but they don't go beyond the target, but they are also not within the target. So these are the ones which are responsible for the sheath field generation. And the fourth are the passing electrons, so which they just leave the sheath field. So they don't contribute actually in acceleration. So what we have observed is that for flat foils, this magnetic field has a very, very good effect. So you can go for from say 20, this is for flat foil, so that without magnetic field, the 20 MeV is the electron proton cutoff energy. You can increase it by like 25% or so. And this again is the result of a focused electron population. So you have a better sheath field, a more focusing sheath field, and also the sheath field survives for much longer in this case. So as you see that the sheath field without the magnetic field, it is very weak as you go for like 250 or 300 femtosecond, but the sheath field with the magnetic field survives, and that is why this, if you look at this cutoff energy with time, you can see like up to 100, 150 femtosecond, this is same, but as you go ahead with time, you see that there is a jump in the acceleration of protons with the magnetic field. So again, because we were interested in structure target, we tried to implement this idea with the structure target. So what we saw that if you apply a magnetic field and you have a structure target, the results are not positives. Why? Because what we see that with the structure target, electrons were already very confined. So magnetic field does not improve it, rather it goes down, the cutoff energy goes down. So this work actually showed that until now the best strategy is to having a normal incidence of laser pulse without the magnetic field and a target with a rectangular groove. Okay, so now the question comes that these are all 2D results, right? So, and you know that in 2D the cutoff energy is overestimated. Why it is overestimated? Because in 2D the electrons, when they go out of the target, they cannot expand in the third direction, right? Okay. So that's why we wanted to explore what is the effect of this 3D structuring. So rather than having just a 2D picture. So what happens that this 2D rectangular groove, it corresponds to two configurations, that you can have a cuboidal groove, which is a rectangular groove in 3D, or you can also have a cylindrical groove in 3D. So both of them correspond to the same the rectangular groove in two dimensions. So we run these simulations, and still we are analyzing some of them. So what we have seen, some results are that these are the parameters which we have used, again using epoch, and the density we have taken as 184. Of course, we are limited by the number of particles per cell because it increases the memory load quite a bit. And the polarization we have tried both linear and circular, but I am having results only for linear here. So we just compared the two geometries, and what we saw that because the waveguides, these are like waveguides, right? So because of the cross section of the waveguides are different, the laser pulse propagation is also very, very different. So what we see that the intensification of the laser, so the intensity of the laser pulse, which is increased as compared to the vacuum value here. So what we see that it is localized only at few points, whereas in case of cylindrical groove, it is extended across the groove. So it continuously pulling the electrons from the side walls very efficiently, and that is the reason we have seen that in case of cylindrical groove, the cutoff energies are much higher. Also, we have looked at electrons, and this is the electron phase space, and you can see that in case of cylindrical groove, the momentum transfer to the electrons is much higher as compared to the rectangular groove or the cuboidal groove. So this has an effect of having a marginally high cutoff energy. It's not very different. So in the two cases, you can see the cutoff energy are very close. And of course, as I said, 2D is highly overestimated. So this is the actual value which we have obtained with this kind of geometries. And currently, we are also trying to analyze these results using waveguide model. But I have not included those results because still we are in the process of that. So to summarize, we have looked at targets with micron size grooves and shown that if you have a rectangular groove in 2 dimensions, that is the most effective one, which corresponds to a cylindrical or a cuboidal groove in 3D. And we have shown that the magnetic field effect is good for flat foils, so it helps a lot. But in case of a structure target, it deteriorates the acceleration of protons. So with that, I thank you all.
Thanks, Vikrant, for this very compact and interesting talk. Now, some questions.
The first question is, what is the the net directions, or I can say net velocity of these ejected electrons?
What is the
net directions of the ejected electrons in this case? Because
so if you have if you have this kind of walls, like if you look at 2D picture, right? So electric field of the laser is a p-polarized laser. So even if you have a little bit of angle in the laser, what happens that the electric field is efficiently, so it's mostly in y direction, roughly y direction, right? So you have a component, a strong component in y direction. So that pulls the electrons out. So because one half cycle it pulls out from the top wall, in the second half cycle it pulls out from the lower wall. And that is why the electron jets are separated by lambda by 2. The alternate electron jets.
Yeah, but when we consider the 3D case, right? Because laser we have 3D, so the sheath formation is all over, right? Laser. So in this case, I think the velocity would be like somewhat in random or what?
No, in 3D case also, I just showed you, right? So what happens, if you look at this picture, these are also electron jets, and we have kind of plotted the whole count of electrons. And you see with X, say sharp peaks and separated by lambda by 2 here. So electrons are basically coming out transverse to the surface of the groove. Of course, with circular polarization, it will be different because then you have a helical path. So electrons are exacted and then they are pushed also in the forward direction. It's like helical motion. But in linear polarization, it's always like that.
So laser field actually pulls the electrons, and then the magnetic field of the laser doesn't play any role.
Yeah, so I showed you. So it pulls the electrons, but J cross B is actually pushing it forward.
That forward.
So it's a kind of in phase, coherent acceleration of electrons in that direction. It's pulling and pushing it in the forward direction.
And then what happens when the laser when these ablations takes place, or does it not?
So that is why we have actually explored different depths, right? So if the thick wall is there, the laser will get reflected, and the electrons will pass the target. So that's how they create a sheath field. But if it's a very thin target, then you have this slit RIT, and if you go even beyond, it will just blow off. So in RIT regime, we saw the optimum results. So electrons can go, and laser is also passing through, so the acceleration is better. But yeah, so that is, I think, one of the reasons that why we have the highest cutoff energy with a thin wall.
Okay. Just a small comment. So when you're grooving your channel, the one which you're completely grooved through, one case, last case, which is not good at the end of the day, you can always make a geometric, remove out the sharpened part on the outside, right? Where the electric fields are concentrated. Can you give me a picture here? You have a case where completely grooved through version of in the 2D plot.
Yeah.
Right. So that's enough. The one before this, for example, the top one, the concentration on the tip when it is grooved through can be geometrically carved out, like we do it in small temperature devices. If you sharpen, if you flatten it by R square, that won't be there, right? Finally, the charging is through.
So what happens that if you look at the electrons which are coming out, so even there, you see that here we have a very coherent acceleration. They just come out, and the sheath field is very well symmetric kind of field.
Correct.
But in this case, these are broken fronts, right? So the electrons which are coming out, they do not create a field which is optimum, the sheath field. Even if we smooth them out, still the field will not be TNSA like of field, TNSA kind of field. Yeah.
Okay, thank you very much.